Welcome back to the EdgeVerse TechCast. This is the podcast that breaks down all of the software tools and enablement, helping developers build what's next at the edge. And I'm one of your hosts, Kyle Dando.
And I'm Bridgette Stone. Today's episode, we're talking about physical AI, humanoid robotics, and a brand new collaboration between NXP and NVIDIA that's designed to make all of this very real for developers.
Exactly. So we've heard a lot about AI models and central compute, but when AI moves into the physical world, well, that's when things get really complex. You're suddenly dealing with everything involved with a modern robot. You have sensors, motors, complex timing. You got to really worry about safety and all that real-time data moving across the entire body of the robot.
And that's where this collaboration comes in. NXP and NVIDIA are working together to deliver integrated real-time robot body solutions built around NVIDIA's Holoscan Sensor Bridge, often referenced as HSB, starting with two reference designs.
And to walk us through the why, the what, and exactly how, we're joined by Altaf Hussain. Altaf works closely on system architecture and real-time solutions at NXP. And he's been deeply involved in shaping these first Holoscan Sensor Bridge ready designs.
Altaf, welcome to the EdgeVerse TechCast. We're very excited to have you.
Thanks, Bridgette. Thanks, Kyle. Great to be here. I'm looking forward to talking about the solutions that we're launching and why we think this is such an important step for physical AI and human robotics.
All right, Altaf, let's start at a high level. We hear the term physical AI a lot, but what makes physical AI fundamentally different from the AI systems people might already be familiar with?
Yeah, so when we talk about physical AI, we're really talking about AI systems that don't just live in the cloud like ChatGPT, but they interact with the actual physical world in real time. So unlike cloud systems, which are purely software-based and are running very large models, physical AI basically is designed to sense, decide, and act, all under very strict timing constraints. So you're dealing with real sensors, real motors, and real safety considerations. Something like a human robot, for example, every joint, camera, encoder, and actuator has to work together deterministically. If that data arrives late or motion isn't synchronized, you don't just get the wrong answer, but you get unstable and unsafe behavior. So physical AI is less about raw computing, but more about predictability, latency, and coordination across the entire system. That's what makes it fundamentally different and more challenging than the AI that lives only in software.
Well, that leads perfectly into my first question. Why does pairing NVIDIA's Holoscan Sensor Bridge with NXP's Edge platforms make sense? How does it solve the challenges that you just mentioned with physical AI systems?
Yeah, so NVIDIA and NXP really complement each other when it comes to physical AI. NVIDIA brings industry-leading AI compute and perception platforms, especially from a vision and multimodal processing perspective. NXP, on the other hand, has decades of experience in real-time processing, secure networking, functional safety, and deterministic control. So NVIDIA's HSB Holoscan Sensor Bridge is a key enabler here because it creates a direct, low latency data path between the parts of the body and the central AI compute. What NXP adds is the ability to implement that bridge in a way that's real time, scalable, and production ready. Instead of pushing everything to a central processor, NXP devices can handle time-critical sensing, pre-processing, and motion control at the edge, while NVIDIA's platform focuses on higher-level AI planning and inference.
Okay, so NXP manages the nervous system and the muscles, while NVIDIA brings the brain to the party.
That analogy is close. It does provide a nice visual on how we work together to manage different parts of a very complex ecosystem. The result is really a clean architectural split that makes it easier to scale. Communicating in real time, providing modularity, more sensors, more capability. Having Ethernet connectivity as part of a modular solution allows you to easily add new sensors, scale up those sensors, replace those sensors, because it's a plug and play kind of approach. And if you need more scalability, you can add more Ethernet ports easily to a system and scale that platform as well. So this is exactly what physical AI systems need, is that scalability and low latency communication in real time to that central compute.
Now, Altaf, this collaboration kicks off with two solutions, a machine vision reference design and a distributed motor control reference design. Why start here?
Yeah, so we thought long about this. We were very intentional about where we started. If you look at humanoid robots or advanced robotic systems in general, the two hardest problems to solve are perception and motion. Perception generates massive amounts of data from sensors and demands very low latency communication so you can process that data. Motion requires deterministic, synchronized control across many different joints. For example, if you're a humanoid, you have your wrist, your elbow, your shoulder, and the rest of the body. All of that motion has to be synchronized. If either of these systems fails, a robot basically fails, no matter how good the AI model is. That's why we started with a machine vision solution and a distributed motor control solution. Together, they represent the two ends of the robot body, sensing and actuation, and everything else builds on top of these solutions. Once this foundation is in place, adding new sensors, new limbs, or new behaviors becomes much more manageable. These aren't just demos, they're actually building blocks for scalable physical AI architectures.
All right, building blocks. I know a lot of our listeners are out there and they like to build things. Let's try to tie this into something that they can work with. What do these two reference designs actually deliver for these listeners that are interested?
Sure. So let's break these down, the two reference designs that we're actually launching. On the perception side, this is a machine vision solution that's based on an i.MX 95, which enables high bandwidth, 10 gigabit, low latency communication in terms of the vision and sensor data to be processed at the edge in the i.MX 95 and also to be sent to the central brain, the NVIDIA GPU pipeline using the HSB Sensor Bridge technology.
Okay, so the i.MX makes a lot of sense for the machine vision reference design. I've seen the very strong history that NXP's had in vision applications. Now, what about the second design for the motor control?
Yes, on the motion side, the motor control solution uses our i.MX RT1180 device. This supports deterministic networking through EtherCAT as well as TSN. This gives us scalability. Many of the humanoid robots have used EtherCAT from a legacy protocol perspective. There's a big ecosystem of motors and solutions that are available that support EtherCAT, but that's limited to 100 megabits per second networking capability. More and more customers are now also wanting to transition to higher bandwidth, lower latency networks like TSN that runs at gigabit speeds. So having a device that can support both protocols and with firmware upgrade, you can basically switch from one to the other, gives you a scalable solution. Also, the network switch allows us to have a kinematic chain or a daisy chain of these devices that can connect together to deliver the full synchronized motion control for a particular limb, whether it's an arm or a leg. So it's a very scalable and modular architecture, giving you deterministic behavior from both a network perspective as well as all the motor control functions that you need all combined in a single device.
Okay, and NVIDIA and NXP have been working together to validate these foundational building blocks. So why would you encourage developers to check out these two designs?
For developers, this ultimately means they're not starting from scratch. They get reference architectures that already account for real-time behavior, networking, safety, and scalability, which dramatically shortens development time and reduces system risk.
And for teams building or researching physical AI systems today, what should they do next? And what can they expect to see from NXP moving forward?
A big part of what we're delivering here is actually software enablement, not just reference hardware. One of the biggest challenges in physical AI systems is stitching together real-time software, networking stacks, drivers, middleware in a way that actually works end-to-end. From the start, these solutions were designed to be HSB-ready in software, not just compatible at an architectural level. On the perception side, the i.MX 95-based solution provides the software for handling camera input, sensor processing, and deterministic data transport to the NVIDIA Holoscan pipeline. The i.MX 95 is currently in pre-production, with production availability coming very soon. The goal is to give developers early access to the software so they can start building and validating their pipelines ahead of launch. On the motion side, the RT1180 platform is already launched and in production and available today. The solution includes software, support for real-time operating systems, deterministic networking, like I mentioned before, TSN and EtherCAT, and synchronized control across distributed motor nodes. This is the kinematic chain. The software architecture is designed to scale, whether you're controlling a single joint, a robotic arm, or an entire human body.
That is great news on the availability of the i.MX 95 and the i.MX RT1180 platforms from NXP. Now, how about the software you introduced? Where will developers find the software?
An important part of this is openness. The reference software for these solutions will be available on GitHub, giving developers direct access to example implementations and system architecture. That transparency makes it easier to understand how these pieces fit together and to adapt them for real-world designs. What developers get is a starting point where the real-time behavior, data paths, and system partitioning are already solved. And instead of spending months integrating low-level software components, they can focus on their application logic, their AI models, and their robot design. And this is just the beginning. You'll see more reference software, more tooling, and tighter integration across NXP platforms as we continue to expand this portfolio, all focused on making physical AI development more approachable, repeatable, and production ready.
So Altaf, this has been a great conversation. Thanks for walking us through not just the collaboration with NVIDIA, but why these first solutions that you outlined and the software behind them really matter for people looking at physical AI.
Yes, Altaf, thanks so much for joining us today and for breaking this down in a way that really connects the architecture, the software, and what developers can actually build.
Yeah, thanks, Bridgette. Thanks, Kyle. It was a pleasure to be here. I really enjoyed the conversation.
For our listeners, we'll include some important links in the show notes so that you can quickly learn more about NXP's HSB solutions and this excellent collaboration with NVIDIA.
Be sure to follow the EdgeVerse TechCast so you don't miss future episodes as these solutions continue to roll out.
And until next time, keep building, keep innovating, and investigate more about the HSB. And we'll catch you on the next EdgeVerse TechCast.